in this discussion, we're going to talk about a technique of integration called integration by parts. And to start with, I just want to have us consider three particular integrals. Consider the integral of e to the x with respect to x. Consider the integral of x e to the x squared with respect to x. And lastly, we'll consider the integral of x e to the x with respect to x. Now, of course, in the first case, the integral of e to the x with respect to x, we know very simply as e to the x plus a constant of integration. In the second case, the integral of x e to the x squared power with respect to x, well, we would use substitution here, wouldn't we? We'd say, let's let u be x squared. And so du is 2x dx. And so we could change our integral a bit where we had the integral, let's say, we need a 2x dx. So I'm going to manufacture my 2x dx. I have to put 1/2 on the, to offset that, a factor of 1/2 on the outside of the integral. And then e to the x squared dx. The e to the x squared is the same as e to the u. The 2x dx is the same as du. So this is simply 1/2 times the integral of e to the u, times e to the u, which of course is x squared, plus our constant of integration. So each of those integrals are integrals that we know how to deal with. The problem is this last one, which looks like it ought to be simpler than the second one, the integral of x e to the x with respect to x. The problem is u substitution will not work. And we really have nothing to substitute there. Oops, will not work. Since we have nothing to substitute, then we've got a real issue. And we don't have a technique. Of course, the technique we're going to use is going to be this technique of integration by parts. So let's develop a little before we go further, and then we'll be able to deal with this particular integral here in just a moment. First, I'd like to remind you of some things that may be evident, may not. But at this point, it's useful to know this. The integral of just dx, well, obviously, we may not see that written in that fashion very often, but it can be. And it would mean the same thing as the integral of 1 dx. And of course, that's just x plus a constant integration. Okay. And yes, we know, I'm going to put this out here, we know we have a plus constant integration. I may forego that for a few instances here. So let's move on then. The integral of dy would then just be y plus, of course, a constant integration. And the integral of dt, of course, would just be t, wouldn't it? It would be just t. Now, here in a moment, we're going to need this information. The integral of, let's say, d, and we could even have a mixture here, something like uv, then that would just be uv. Okay, that's the idea behind this that we're going to use in a moment. Okay, now maybe I've made some sense, maybe not. Here's what we know. That suppose we have a product of functions u and v. And let's suppose that we're asked to take the derivative of that product with respect to v. So we're taking the derivative of u times v with respect to v. Of course, u and v are functions. Well, first we would say take the first function and multiply it with the derivative of the second. Well, the derivative of v with respect to v is just 1, isn't it? And then we would add to that the second function times the derivative of the first. And the derivative of the first would be the derivative of u with respect to v. Now, let me clean that up here just a moment, okay? Let me again write this as, in fact, let me write it a little differently yet. Let me write this as the derivative of uv in this fashion with respect to v is equal to, well, rather than saying u times 1, of course, I'll just say u plus v times derivative of u with respect to v. Now, although we don't normally think of these derivatives as fractions, they really do come from fractions, and those parts, those d parts, are called differentials, which of course you studied in Calculus 1. Let's imagine multiplying through by the differential dv. If we do, then we're left with duv on the left side is equal to u dv on the right side plus v du. Okay, well, now what I would like to do next is integrate all the way through. We'll integrate the left side, and we'll integrate the right side. Well, when we integrate the left side, okay, we're just integrating both sides. This is what we're integrating. And when we integrate the right side, we're integrating a sum, which of course is the sum of the integrals. So we have the integral of u dv plus the integral of v du. Now, as we discussed up above, the integral d whatever is just that variable or variable expression. So on the left side, we simply have uv. And on the right side, we have the integral of u dv plus the integral of v du. Well, what I would like to do next is I'd like to actually subtract this from both sides and rearrange at the same time. When I subtract this from both sides, I end up with uv minus the integral of v du, and that's left on the right side just the integral of u dv. And that's really what I want to write down here, except with the integral of u dv on the left side. The integral of u dv is equal to uv minus the integral of v du. This is something you need to become very familiar with, this little formula, if you will. Let's go to the next page and see how we actually use this idea. So like I said, I want to go back to that problem a moment ago that we didn't have any luck with. And we're going to use integration by parts. That's what we're doing here, integration by parts. And here's the idea behind integration by parts as we get started. Here's the integral that we're dealing with. Okay, and what we're trying to do is model that with what we had just a moment ago. The integral of u dv is equal to uv minus the integral of v du. Here's the idea. We're wanting to trade in one integral, that's the integral of u dv, for another integral, the integral of v du, which we can actually calculate. And so we're modeling what we have. We're trying to match what we have so that, if you will, do substitutions so that we can replace our integral. We need to, in our integral, decide what u is and decide what dv is, and then use that information to calculate the integral. That is, then if we can do that with it's uv minus the integral of v du. Now, key is to make the right choice. Let me write a few notes here before we move on. Now, as we're looking here, as I've noted, we're trying to equate our ex dx with u dv. And the key is to make the right choice for dv. And let me tell you that dv is usually the most complicated. It's so saying dv is usually the most complicated factor in the product that can be integrated by a known method. Now, what product am I talking about? X dx dx, x e to the x dx. So as I look up there, I've got, oh, and by the way, dx, and this will make sense in just a moment here, dx always always is included with dv. And we'll see why in a moment. Now, remember, what we're trying to do is name u and name dv. Okay, that's what we're trying to do. So we're looking at dv, and we want to name it from above, and we're looking at the most complicated of the factors, x and e to the x. And clearly in this case, e to the x is the most complicated. And so we need to name dv. Well, okay, dv, we're going to name e to the x. And remember, as I just said, it always includes the dx. And you'll see why in just a moment. Well, then the only part left for us is to name u. And if we look above, well, the only part that's not included so far is x. I mean, that's the whole issue. Is so we would name next. That just leaves us with u being x. Now, I will also tell you that the right choice that I was saying above, the right choice, is usually a matter of hindsight. We'll get more rules and indicators of how we might do, but it's usually a matter of hindsight, because here's what we're trying to do. Remember, it seems like I'm putting off doing something. The question ends up being, is the integral v du less complicated than the integral we started with, which was the integral of u dv. Okay? That is, can we integrate the integral of v du? That's the whole issue. Well, what is the integral of v du? Okay, well, let's go back above now. What we've named, see, here's where we are. We say we've got the integral of x e to the x dx. Okay, that's what we've got. Now, if we name xu and we name e to the x dx dv, then this is nothing more than the integral of u dv. That's the whole idea of that substitution. Now, having the integral of u dv, the integration by parts technique says this is going to be u times v minus the integral of v du. So that's where we are. If we can integrate the v du, but now of course we don't know what v is and we don't know what du is. So to use this formula, we've got to calculate all of the pieces that we need, u and v and du. So we do that from our named information. That is, dv, remember, was the integral, e to the x dx. Now, to find v, we integrate dv. If we integrate dv, that gives us v. But of course, if we integrate dv, we've got to integrate e to the x dx. And so from that first choice of dv, this integral tells us that v is equal to, well, of course, the integral of e to the x is just e to the x plus a constant integration, but we'll wait until the very end to deal with that. So now we know dv, okay, but we also know v, and we need that in the formula. Now, the other part of our substitution was that u is equal to x. So what we do here is we take the derivative of both sides with respect to x. Of course, the derivative of u with respect to x, we write du dx, and the derivative of x with respect to is 1, and we would have done this in another way previously anyway when we're doing substitutions, but now we know that du is equal to dx. So we have something for u, we have something for v, we have something for, and so on. So we go back to our formula. Well, u is x. So we put x in this place. V is e to the x. So we replace v with e to the x minus the integral of v. Well, v is e to the x. du. Oh, well, du is dx. We have that right down here. And this is what I meant a moment ago. This is usually a matter of hindsight. Did this help us? Did our choice of dv and our choice of u give us an integral v du that we could actually integrate? And here we can, can't we? The integral of e to the x dx is just e to the x. So now we can write this as x e to the x minus the integral of e to the x with respect to x, which is just e to the x, plus, of course, finally, our constant integration. So we've succeeded in integrating x e to the x with respect to x. This is the result. And, of course, we could easily check this. Okay, we could easily check this by calculating the derivative ourselves, and maybe here in a moment we will do that. Now, and let's, the bottom line, and all the notes I've been making as we go along here, is this works only when our choice of dv is easily integrable, because we have to do that to find v. So we had to find the integral of dv. And so if our choice of dv we can't integrate, then that's not a good choice. And of course, the new integral, that is the integral of v du, after we figure out what v and du are, that integral is easier than the one that we started with. And so those are important concepts as we go through this. Now, I guess it might be worth looking on the next page that we could have made a wrong choice here. Again, here, as I was saying, for the integral of x e to the x with respect to x, a wrong choice would have been, or not a good choice, would have been making dv x dx and u equal to e to the x. I mean, remember what we're doing. We're trying to model against this. We've got the integral of x e to the x dx. And so what we could have chosen is for dv to include the x, and it would always have to include the dx, and then we would have the only thing we would have had left for u would have been just the e to the x. Okay, so if we use that model, okay, then of course we would have the integral of x e to the x dx is equal to the integral of u dv, which would be uv minus the integral of v du. Okay, that's what we would have. Now, when we go to find dv, that is, dv is equal to x dx, well, certainly that is something we can integrate, so that's not a problem. The integral of dv will be the integral of x dx. Of course, the integral of dv is just v, and the integral of x dx is 1/2 x squared. Now, on the other hand, if u is equal to e to the x, then it's no problem to find du. That's the derivative of e to the x times dx, which is just e to the x dx. And so we can accomplish finding v and du very quickly, but the problem would be that when we substitute these values back in, our u is e to the x, and our v is 1/2 x squared. So I'm going to write the v first, 1/2 x squared, and our u e to the x. And then we have minus an integral, and this time our integral is v 1/2 x squared times du, if you will, which is e to the x dx. And so the integral that we have here is, if I would say anything, it's more complicated than what we started with. And we don't have any better idea how to integrate that than we did what we started with. And so this wasn't a good choice. And of course, what went wrong, remember in the very beginning, we said to make dv as complicated as possible, but where we can still integrate it, okay? Where we can still integrate it, because that's what we do on this step, isn't it? So we didn't make dv very complicated here. Now, let's do one more thing before we leave this problem, and then we'll look at some more. Check our answer. Check the answer. Remember, we said that the integral of x e to the x dx is equal to x e to the x minus e to the x, plus our constant integration. Of course, the way we check it is seeing if the derivative of our answer is our integrand, is x e to the x. So we would take the derivative with respect to x of our answer, x e to the x minus e to the x plus our constant integration. And of course, as we're integrating that, we first find differentiating, we'd first find the derivative of x e to the x, and then subtract the derivative of e to the x, and of course then add the derivative of our constant. But of course, the derivative of the constant is 0. Now, the derivative of x e to the x would have to use the product rule. So we'll say the first function times the derivative of the second, and the derivative of e to the x is just e to the x. And then we'd say plus the second function times the derivative of the first, and the derivative of x with respect to x is just 1. And then we have minus the derivative of e to the x over here, and of course that's just e to the x. And then plus our 0 here at the end. And you notice that in this 0, okay, if you notice here, we really have e to the x minus e to the x, which is just 0. So the result is x e to the x, which is in fact our integrand, and so we've checked that we did do it correctly. Well, we've seen one simple example here, and of course I'd led us right into it that that's what we were going to do. There's a big question. I mean, tests will come up. We're going to look at a lot of different techniques for integrating. This is one of several. And so the big question is, when do we use integration by parts? And this is a very serious question. When is it a consideration? Well, the answer is many times we will use and we'll want to investigate when we're integrating products that include transcendental functions. Maybe you wondered why our book was called Early Transcendentals. Well, transcendental functions are functions like e to the x, our trig function, sine of x, cosine of x, tangent of x, and so on. Logarithmic functions like natural log of x, inverse trig functions like inverse sine of x, and remember sometimes that's called arc sine of x, depending on your book, and etc. Those are all transcendental functions. And so in the example we just looked at, where we had the integral of x e to the x, well, the idea here is that we have a product that we're integrating, and one of the, at least one, sometimes it's more than one of the factors is a transcendental function. In this case, it was e to the x. So that's a good guideline for when we might want to try it. Well, let's look at another example here. Okay, we'll do that on the next page. Okay, in the second example, we're asked to evaluate the integral of x cubed times natural log of x with respect to x. Once again, what we're trying to do is convert this integral of x cubed natural log of x dx, into a form that is the integral of u dv. So we have to name a u, we have to name a dv, and normally we name the dv first. So let's just kind of go through what our choices are. Okay, we could name dv natural log of x dx. Certainly we could do that. Remember, it always has to include the dx. We could name dv x cubed dx. We could name dv just dx. That's something that I haven't discussed before, but we could name it just dx. But of course, naming it just remember, it has to include, dv has to include dx. So if we named dv just x, then we would have u as x cubed natural log of x. If we named dv x cubed dx, then u would be just natural log of x. And in the case we named dv natural log of x dx, then the u would be the x cubed. Now, remember I said we choose dv to it be as complicated as possible, but which we can still integrate. And this first choice, I don't know how to integrate natural log of x. So that's a problem choice. Now, this choice is not very complicated. We can certainly integrate it, but this looks like the most complicated choice that we can actually integrate. And so that's what I'm going to choose. So here's the setup. I'm choosing dv to be x cubed dx. Now once I do that, that only leaves me the choice for u to be natural log of x, because we have to take up all that space, don't we? And we have to accommodate all the pieces. Now, to find dv, we integrate, and in the future I might forego this, but we integrate both sides. That is, I might just say v is equal to the integral. So the integral of dv is just v, and this is what I'm saying. So I might in the future just say v is the integral of x cubed dx. Now that integral we can complete without much difficulty, can't we? That is going to be 1/4 x to the 4th. And on the other hand, when we have this u is equal to natural log of x, we're going to need to know du. And so the derivative of u with respect to x, that is the derivative of natural log of x, is just 1/x. So du is 1/x dx. Now, we go back to our integral, the integral of x cubed natural log x dx, being the integral of u dv now. See, it actually matches. U dv is what we've got. If we make this our dv, we've got the x cubed dx. If we make this our u, we've got the natural log of x. Okay. Well, our formula says we can integrate that by saying uv minus the integral of e du. And so we need to let me come back over here so I have space. We need to replace our u with natural log of x. And we need to replace our v with 1/4 x to the 4th. And then we have minus. Now here's the drum roll. Is this integral we're getting ready to write down one that we can deal with? Well, we have v, which is 1/4 x to the fourth, and du is 1 over x dx. Well, that looks like something that we probably can deal with. Let's go a little further. Let's rearrange this first term. I'm going to write it as 1/4 x to the fourth times natural log of x. And in this integral, here's what we're going to have. I'm going to factor out that 1/4, and I'm going to have an integral of x to the fourth times 1 over x. Well, that's, of course, that's x to the fourth over x, which can be simplified, can it? That's just an x cubed. So we'll go through and clean up a little bit more. You know, we're really integrating just x cubed here with respect to x. Well, the integral of x cubed we have no problem with. So we go back and we rewrite some more. Now here's our original 1/4 factor outside the integral, but when we integrate x cubed, we will get a 1/4 x to the fourth. And finally, we put our constant integration. And of course, we'll finally clean this up by multiplying those two 1/4s together. So we have 1/4 x to the fourth times natural log of x minus 1/16 times x to the fourth plus our constant integration. There is our result. Well, that was kind of interesting, wasn't it? Okay, let's do one more, and then I'll give you another guideline that can be useful to us. We'll do that on the next page. Okay, here we're asked to evaluate our third example, evaluate the integral of x times arctangent of x with respect to x. And remember, and depending on the book that we're working from, arctangent of x is the same as inverse tangent of x. So maybe I'll write it this way. Okay. So we've got the integral of x times inverse tangent of x. And of course, once again, we're trying to make this look like the integral of u dv. And why? Well, and I missed it in example 2. We have a product of two functions, x and inverse tangent of x, one of which is a transcendental function. In the last example, we had the integral of x cubed times natural log of x, and of course natural log of x is a transcendental function. So it's not surprising that we would try integration by parts here. Now, remember, our deal is to choose, the whole thing is to choose dv. And we want to make dv as complicated as we can, but while everything else still works. So when I'm looking up there, one of the most complicated choice I can make for dv would just make it be arctangent or inverse tangent of x dx. Remember, dv always includes dx. Now, another possibility would be to choose dv to be the x dx, and then yet another possibility would be just choose the dv to be dx. That kind of sums up our possibilities, I think. But this is similar to our last example. Although making dv inverse tangent of x dx, that's the most complicated dv, I don't think that we know how to integrate inverse tangent. I mean, you can pause here and think about that and see if you can figure out how to integrate inverse tangent, but not so much, I don't think. I don't think we can do that. The last two choices, then, of course, dv equal x dx is the more complicated of those two choices, and we can easily integrate x dx. And so that's a reasonable choice. Now, let's do that. This is what we're choosing to do. We're going to make dv x dx. And we're going to make u inverse tangent of x. Those are the choices. Well, in the case of dv, we integrate dv, we get v. So we have v is equal to the integral of x dx, and obviously the integral of x is 1/2 x squared. So we have v is equal to 1/2 x squared. Of course, now we have to find the derivative of u, don't we? Which means we have to find the derivative of inverse tangent. And maybe you remember that. I hope you do. If not, you need to go back and review. The derivative of inverse tangent of x is 1 over 1 plus x squared, or we could say 1 over x squared plus 1. And so du is 1 over 1 plus x squared times dx, isn't it? Okay. Well, now we're ready to, that looks kind of scary, I suppose, but now we're ready to deal with our integral of x inverse tangent of x dx, as we have that as the integral of u dv now. We have that set up. And of course, whoops, and the integral of u dv, pardon me with my messy equal sign, is uv minus the integral of v du. Okay. Well, u, of course, is inverse tangent of x, and v is 1/2 x squared. So let me go ahead and reorder the way I'm writing that. I'm writing, of course, the v first and the u second in this product, minus the integral of. Okay. Now what do we have? The integral of v du, and v is 1/2 x squared, and du is 1 over 1 plus x squared dx. Well, this might give us a pause. Let's rewrite here. 1/2 x squared inverse tangent of x. We'll factor out the 1/2 factor in this integral. And so what we have left is an integral of x squared times 1 over 1 plus x squared. That is x squared over, let's write 1 plus x squared as x squared plus 1 for our purposes here. And that's a little bit of a problem itself, isn't it? This is an inverse tangent there. Well, I made it worse. Here we have one of the techniques we saw earlier, I think, in our basic techniques, is that we could actually do some long division here because this is not a proper fraction. Okay, we have our degrees being the same. And so if we use long division on that, maybe we have something that we can deal with a little better. Now, I'm a little bit out of room here. I wish I had some more space. What I'm doing is I'm going to divide x squared plus 1 into x squared. And of course, to do that, I need to multiply by 1. I'm trying to, what do I multiply x squared by to get x squared? So I'm going to multiply by 1. And usually that would be way over here. And when I do that, I get 1 times x squared plus 1. And then I'm going to subtract. Well, then I get x squared minus x squared, which is 0, and 0 minus 1, which is negative 1. And so what this tells me, these two pieces of information tell me that x squared over x squared plus 1 is nothing more than 1 minus 1 over x squared plus 1. Okay? Okay, so let's rewrite then. Here's where we are. Okay, this information is going to help us do that second integral. Make sure you understand this long division. So what we've got now is 1/2 x squared inverse tangent of x minus 1/2. Now we're replacing x squared over x squared plus 1 with the divided result, which is 1 minus 1 over x squared plus 1. So to complete this, we just need to be able to complete that integral. Well, of course, we're going to make that two integrals. We've got our minus 1/2 factor on the outside, but now we have the integral of 1 dx minus the integral of 1 over x squared plus 1 dx. And of course, the integral of 1 dx is just x, isn't it? So we have 1/2 x squared times the inverse tangent of x minus 1/2. Now in these brackets, the integral of 1 with respect to x is just x. And then we recognize, oh, the integral of 1 over x squared plus 1 is nothing more than inverse tangent of x. And finally, plus our constant integration. Now, we could clean this up quite a bit by distributing that 1/2, that negative 1/2, if you will. So let's do one more line here. We have a 1/2 x squared times inverse tangent of x. Now, negative 1/2 times x is minus 1/2 x. Negative 1/2 times a negative inverse tangent is plus 1/2 inverse tangent of x, plus a constant of integration. So we had to kind of use another technique in here to accomplish what we were trying to do, that second integral. Although it wasn't simple, it was one we could accomplish. So we could be proud of ourselves for getting this job done. There's our result. Before we proceed, I'm going to introduce the Wyatt rule, I don't know how you pronounce that, but it's a rule of thumb proposed by Herbert Kasubi of Bradley University that tells us, as a rule of thumb, how we might choose u and dv. Okay? And it states that whichever function whichever function comes first in the following list should be u, and whichever comes last in the list should be dv. And the list looks like this. The L stands for logarithmic functions. And logarithmic functions would be things like the natural log of x, or even some other base, the log of x, some base other than e, and similarly, etc. I stands for inverse trigonometric functions like arctangent or inverse tangent of x, inverse sine of x, etc. And A stands for algebraic functions like polynomials, x to the second power, 3x to the 50th, and it could be a polynomial even with multiple terms. The T is for trigonometric functions such as sine of x, tangent of x, etc. And finally, the E is for exponential functions, where the base is E, for instance, like e to the x, or of course we have bases, other exponential functions can have bases other than e, like a 2 to the x or a 19 to the x, etc. Now, if you stop and think about the three, and remember how this goes. The further in the list that the functions go is, that's what we should call dv. We're comparing the functions we have in our integral. And the earlier in the list would be the u, the later in the list would be the dv. Let's do a real quick review of what we've already done and see how it does fit this. Okay, the very first integral that we looked at was the integral of x e to the x dx. Now remember, I'm looking down the list. Here's what I've got. I've got an x and I've got an e to the x. X is an algebraic function. E to the x is an exponential function. The exponential function comes later, so that should be the dv. The algebraic function x comes earlier, so that should be u. The earlier in the list is the u. The second one we looked at was what? The integral of x cubed natural log of x with respect to x. We look down the list. Let's see. And what did we choose, by the way? If you remember, we chose the dv to be equal to x cubed dx, and we chose the u to be natural log of x. Okay, so we've got a logarithmic function and an algebraic function. The algebraic function is further down the list, and so that's the dv. That's why x cubed dx is the choice. The natural log of x is earlier in the list, so that's u. Okay, and it worked in that case as well. Okay, the last one we looked at was the integral of x arctangent of x with respect to x. Or we turned that into inverse tangent, didn't we? We called that the integral of x times the inverse tangent of x. Different notation, but same function. Okay, well, if you recall, what we chose there was we made dv equal to x dx. And we chose u to be the inverse tangent of x. Now, again, as we look, we have an inverse trig function and we have an algebraic function. The algebraic function is further down the list, and so that's our dv, and that's what we decided. The inverse trig function is earlier, it's first in the list, and so that ends up being our u, and that's what we ended up deciding. So this is a rule of thumb. It is not always useful, but let's see how we would apply it then on the next page. Okay, we're to evaluate, in this case, evaluate the integral of x cosine x with respect to x. Now, I would tell you that in my old method, the one I started with, what I was telling you about, is we would normally choose the dv to be as complicated as we could, and we could still integrate, and that would mean I'd choose dv to be cosine x dx. But for the like rule, let's look at what the rule tells us to do. We have a algebraic function. Okay, let's write down L-I-A-T-E so we can remember this. We have an algebraic function, and we have a trig function. Okay, now remember, the further down the list, the earlier is the u, the latter is the dv. So our cosine x being the trig function is the latter, that's the dv. And of course, the dx has to be included, and so that we're going to choose dv to be cosine x dx. And so that leaves the u, the algebraic function, which is earlier in the list, to be our x. Now, as we integrate dv, we get v, and as we integrate cosine x dx, we simply get sine x. And as we differentiate u with respect to x, we get du is equal to 1 dx, or just dx. And so now we've got all the pieces that we need. The integral of x cosine x dx, as we've set it up, this is the integral of u dv. And we know that that's u times v minus the integral of v du. And now we have all the pieces in place. Our u value is x, our v value is sine of x, minus the integral of v du. Well, v, of course, is sine x, and du is dx. And that is an easy integral for us to complete. So So we have x sine x minus the integral of sine x, which is negative cosine x, isn't it? Of course, plus our constant integration finally. So we get x sine x plus cosine x plus our constant integration is the result. Now, like I said, this is a rule of thumb only. It's not always going to work. In fact, let me have you see another example here. Okay, here we're asked to evaluate the integral x cubed e to the power x squared dx. Now, if we tried to use light, okay, let's make a point here. If we tried to use light, we're looking at an algebraic function, which is x cubed, and we're looking at an exponential function, my bad, which is e to the power x squared. And so that would tell us that we're going to choose dv to be e to the power x squared dx, and we're going to choose u to be x cubed. And the problem here is when we try to calculate v, we would have to know what the integral of e to the x squared with respect to x is, and that is a problem. Of course, du wouldn't be any problem. That would be 3x squared dx. But this is a problem, and so in this case, we can't simply rely on this rule. In fact, if you're interested, here's what we would have. This would require being a little bit we'd have to be somewhat clever, if you will, here, and sometimes that's what it requires, is cleverness. What I would first do in this case is, the reason I can't integrate to get my dv, I've got an integral of e to the x squared dx, and that's the problem, because I can't use substitution there. If I had x times e to the x squared, then I could integrate. And so what I'm thinking that I will do here is I'll rewrite this integral so that it's x squared times x e to the x squared power dx. Now, if I do that, then what I would choose to be dv, okay, I'd make dv now x e to the x squared dx. And I choose u to be x squared. So that tells me that my v would be the integral of x e to the x squared dx. And and we could complete that. That would be what? By substitution, if I let u be x squared, wouldn't we have 1/2 e to the x squared is that integral? Yes, it is. Okay. And we could calculate du, which would be 2x dx. And so under those circumstances, that's a little twist on what we'd done earlier, but under those circumstances, of course, we've got the integral here of u dv. And we know because of integration by parts rule that that's uv minus the integral of v du. Which, again, that needs to be memorized. We've got to do that over and over. So we have a u times a v. Well, our u is x squared. Our v is 1/2 times e to the x squared power. Minus our integral of v du. Well, of course, our v, once again, is 1/2 e to the power x squared. And we're kind of holding our breath here. I hope this is going to work. And our du is 2x dx. Well, look at that. We got fortunate. Let's rewrite this integral of this product at the front, and let's write it as 1/2 times x squared times e to the power x squared. And in the second case, I guess we have in this integral, we have a 1/2 times a 2. So we end up having the integral of x times e to the x squared power dx. And we just saw a moment ago that that integral is 1/2 e to the x squared power. So we end up with 1/2 x squared e to the power x squared minus this integral, and we're kind of fortunate that that worked out, minus this integral, which results in 1/2 e to the x squared power. And of course, plus our constant of integration. So occasionally we have to be clever. We still used, and once this cleverness occurred, we still did let the dv be the most complicated part of the integrand that we could actually integrate. We just needed to borrow, if you will. Well, now we're going to begin to look at some little twists and turns that we have to be familiar with when we're dealing with integration by parts, because sometimes it's not always quite so straightforward. So I've titled this example because we're going to see something a little different here, using integration by parts in succession. Evaluate the integral x squared cosine x dx. Now, if we follow the pattern that we've been following, remember with the most complicated part here that we can actually find the integral of is the cosine x. So I'm going to, or we could go through this light again, okay? We have an algebraic function, which is x squared, and we have a trig function, which is cosine x. And so keeping that in mind, since the cosine x is further down the list, that would be our dv. And that's what I said all along anyway. Pick the part that we can integrate, the most complicated part that we can integrate. So we'll let dv be cosine x, and we'll let u be the x squared. Okay? Well, in this case then, when we integrate dv, we get v, and when we integrate cosine of x with respect to x, we simply get sine of x. And of course over here we have du is 2x dx. Now we've done this, something that looked like this previously, but it's a little different here, I think. Yes, what we integrated before was the integral of x cosine x, not x squared. Okay. Well, then that sets us up. We can begin the process. So the integral of x squared cosine x dx we have written as the integral of u dv, don't we? And I'm going to come on across here just so we can say, oh, that's uv minus the integral of v du. Okay. And I'm going to come back here. I just wanted to use that space so I didn't take up so much vertical space. Okay. Well, anyway, here's what we've got. A u times v. U is x squared, and v is sine x. Everything's smooth so far. Minus the integral of v du. Now, the v is sine x, the du is 2x dx. So I'm going to rewrite it a little bit. I'm going to write it as 2x times sine x dx. I've just kind of reordered it, but that's all I've done. And of course, we might want to kill a little bit of time here while we're thinking about what we're going to do. We can certainly factor out that too, can't we? Now, unfortunately, we don't know how to integrate x sine x so easily. But here's the idea of succession. That what we've accomplished, if you notice, we went from an integral of x squared times a trig function to the integral of x to the first power times a trig function. So in a way, we got better. That is, the power on x went down, it's not quite as complicated. So we reconsider this single integral. If we're going to work on, we can't integrate that directly, but maybe we can use integration by parts again. And so for this integral, okay, so for this integral, we need to think of our u and dv for this integral. And so I would propose here that we let dv be sine of x, and we let u be x. And so in this case, we get v is, sine of x dx, my bad. The integral of sine x dx is negative cosine x. and the derivative of u is just 1, so du is 1 dx, or just dx. And so now I can use my integration by parts formula on this integral, and we can fill in. The u is x, the v is negative cosine x, so let me write that negative x times cosine x, minus the integral of v, which is negative cosine x, du, which is dx. Now I've got a negative and a negative there, so I can factor out that negative from the integral. And so I have plus the integral of cosine x dx. And of course that ends up being what? Just sine of x, doesn't it? Okay, plus sine of x, plus our constant of integration. But I'm going to forego that for just a moment. Now, remember what we've done. We calculated this integral, and that was the part of what we had been doing a moment ago. So here's where we are. The integral, the original integral we're trying to find is the integral of x squared cosine x dx. And we had gotten it to the point where we have x squared sine x minus 2 times the integral of x sine x dx. We just determined the value of that. So let's put its value in. So we have x squared sine of x minus 2 times the result of that integral, which was negative x cosine x plus sine x. And of course, we finally have our constant of integration. So as we do a little distribution here with that negative 2, we get x squared sine x plus 2x cosine x minus 2 sine x plus our constant of integration. So we had to use integration by parts, if you will, in succession or twice in one problem. On the next page, I'm going to give you a little bit of heads up here, kind of a summarization of this problem before we move to the next problem. So my summary is this. For integrals of the following forms that I'm getting ready to write, these will require using integration by parts in succession and sometimes multiple times for integrals of the following forms. I should have just said integrals of the following forms. I apologize. And here are those forms. Let's look. If we have the integral of a polynomial, that's the reason I'm using p, times sine of kx with respect to x. Or if we have an integral that's a polynomial times cosine of k times x. K is just some constant. Or if we have the integral of a polynomial times e to the power k times x. That's a k, which is a constant. In all these cases, k is a constant. So as an example, okay, there's a few examples, we might have the integral of x to the 4th power times the sine of 3x with respect to x. Something that might look like that. Or we might have the integral of 3x squared plus 5x plus 1 times e to the 4x power. Okay? A polynomial times e to a constant times x power. Okay. So first, k is a constant. In all of these forms, just as a note, p of x is a polynomial of some degree. I'm going to say of degree n, like in x to the 4th, of course, the degree is 4. we've seen examples. The last example was the integral of x squared cosine x dx. And in that case, of course, the polynomial is x squared, degree 2. And cosine x, of course, the k was just 1. Now, here's the note. These will require integration by parts n times. Remember what n is. N is the degree of that polynomial. So in the example we looked at, the integral of x squared cosine x dx, we had to use parts twice. And that twice was because of the x squared. And so if you recall, what happened is the first time around, the power went down to x to the first. And that was the whole issue as you stop and analyze this, is that we were taking, we called the u the polynomial, didn't we? And so when we took the derivative, the power decreased, and that's what happened there. So in the case of something like the integral of x to the fourth sine of 3x dx, we would have to use parts, would have to be used 4 times. Each time we used it, we would have a power on x go down, and until we finally got x to the 0 power. That's the whole point. When we get x to the 0 power, we can deal with it. Or, of course, in the case that our polynomial is something like 3x squared plus 5x plus 1, in that integral, okay, if we did something like that, of course, the polynomial is what we name the u. And if we name the u the polynomial 3x squared plus 5x plus 1, we're going to have to use parts, would have to be used 2 times, okay, because the degree of that polynomial is 2. And every time we used it, the degree would reduce. We'd get a simpler and simpler polynomial. So that's a good thing to know about. When you start looking at these, you'll know how many times you're going to have to use integration by parts if you see one of those forms. Okay, let's look at another little twist, or maybe quite a big twist, quite frankly. But let's look at another twist and see how we can deal with this next problem. Okay, you can see in this next example where I've titled it again, Solving for Original Integral, which I agree doesn't make much sense, but here's what we're to evaluate. And we'll see why it makes sense in a moment. We're to evaluate the integral of e to the power of 2x times cosine of 3x with respect to x. Now, if we're actually, here's a case where we don't really need to use Lie-8. And I'll tell you in a moment that we can do this a couple of different ways. But if we were to use that, let's see, we have an exponential function, which is e to the 2x, isn't it? Okay. And we have a trigonometric function, which is cosine of 3x. And so the exponential function occurs last, and so that's going to be our dv. So our dv is e to the 2x dx, and our u is cosine of 3x. Now when we integrate dv, we get v. And when we integrate e to the 2x with respect to x, we get 1/2 e to the 2x. And over here in the case of u, when we find the derivative of u, the derivative of cosine, of course, is negative sine. And so this is actually going to be a negative 3 times the sine of 3x dx. And you can verify that. I'm sure that you understand what we're doing there. the 3 comes from the derivative of 3x, doesn't it? Okay. So, we're ready to go. That is, we have the integral of e to the 2x cosine of 3x with respect to x. We've written it as the integral of u dv. And so we know that that is equal to u times v minus the integral of v du. For a purpose, well, let's just go further here. So as we write this, u times v, well, you see above our u and v, and I'm going to rearrange it while I'm doing this. I'm going to say v times u actually. 1/2 times e to the 2x power times cosine of 3x minus the integral of v du. Now, of course, v is 1/2 e to the 2x power, and du is a negative 3 sine of 3x dx. Now, I'm sure you're looking at all that, but I'm going to clean up a little bit first here. We have 1/2 e to the 2x times the cosine of 3x. And I'm subtracting an integral that has a negative 3 factor in it. In fact, I have a negative 3 times a 1/2 inside, don't I? So I'm going to factor that out, and so that negative of a negative is positive. So I have a plus 3/2 outside the integral, and an e to the 2x times sine of 3x with, with respect to x dx. And I don't blame you. I'm looking at this and saying, man, I didn't do any better. I mean, I just changed a cosine for a sine, and I still don't know how to integrate that. But bear with me. And because of the cyclic nature of cosine sine when we integrate or when we differentiate, in either case really, when we integrate or when we differentiate, we go back and forth from sine to cosine, cosine to sine, and so forth. And that's going to pay some dividends here. So what I want to do is concentrate on this integral temporarily, okay? And I'm going to do the same thing that I did above. I'm looking to integrate e to the 2x sine of 3x. We're putting the other on hold temporarily. And to do that, I'm going to choose dv to be e to the 2x, just like I did a moment ago, dx. And so v, once again, is 1/2 e to the 2x. And I'm going to choose u to be sine of 3x. Well, although I chose it to be cosine of 3x, but that's because I had a cosine. And so du, derivative of sine, is just cosine. And then we have to say times the derivative of 3x, which is just 3. So we get 3 cosine 3x dx. I'm sorry, I'm out of room there. So as I go to integrate this, okay, I've got a u times v. So the same kind of thing I had before. This is the form u dv. And of course, that integrates as uv minus the integral of v du, the new u and new v. So down below, I'm going to write that. The u times v this time, I'm going to write it as v times u, is 1/2 e to the 2x power. And the u is sine of 3x. Minus an integral. And the integral is 1/2 e to the 2x. The integral is v du. And v is 1/2 e to the 2x. And the du is 3 times cosine of 3x. And you're already panicking. I hope you are, because it looks like we're going in a circle. Well, let's clean this up. Cleaning this up, let's see, I've got a 3/2 factor inside, so this is minus 3/2 times the integral of e to the 2x cosine of 3x with respect to x. And rightly so, you would say, well, that's right back where we were. Are we going to just do this again? And the answer is no. Here's a little, we need to write it all out so that we're going to see what happens. But you'll see that we started out with the integral of e to the 2x cosine of 3x dx. And we are kind of right back there, but let's write down this right side. You know, when we're looking above, what we had was a 1/2 e to the 2x power cosine of 3x plus 3/2 times that integral e to the 2x sine of 3x. And in the next step, we showed that that integral was all of this. So let's write it in there. We'll have a 1/2 e to the 2x sine of 3x minus a 3/2 integral of e to the 2x cosine of 3x dx. I've kind of ran myself out of room again, didn't I? Let's come down here so that I can see. Let's clean up that right side by distributing that 3/2. So I'm just rewriting. Okay. Now 3/2 times the 1/2 e to the 2x, so on, that's a 3/4, isn't it? So we have a 3/4 times e to the 2x sine of 3x. Now we're going to multiply the 3/2 with the minus 3/2 times the integral. So that's going to be a minus 9/4 times the integral of e to the 2x cosine of 3x with respect to x. Now, again, you're still thinking we haven't gotten anywhere. But notice, and the secret really is the fact that we have a minus sign right there. If we take this whole expression, if we add that integral to both sides, you'll notice that we'll end up with that integral being only on the left side. So I'm adding 9/4 times the integral of e to the 2x cosine 3x dx to both sides. So I'll have my original e to the 2x cosine 3x dx plus 9/4 times the same integral. That's because that's what's on the right side. Now when I add that to the right side, then that integral doesn't show up any longer. And what I have left on the right side is 1/2 e to the 2x cosine of 3x plus 3/4 times e to the 2x sine of 3x. Now the whole significance is what we have right here. Because we have one of these integrals plus 9/4 of those integrals, well, how many altogether? 1 plus 9/4. Well, 1 plus 9/4 is 13/4. So we actually now have this to where we can say that it's 13/4 times the integral of e to the 2x times cosine of 3x dx is equal to 1/2 times e to the 2x cosine of 3x. Maybe you see where I'm headed now. 3/4 times e to the 2x times sine of 3x. And where I'm headed is to multiply both sides by that reciprocal, the reciprocal of 13/4. And if I do that, then I'll have that integral on one side alone, okay? So I'm going to multiply both sides by the reciprocal of 13/4. And when I do this, it becomes 1 times e to the 2x cosine of 3x with respect to x. But over here, I'm multiplying by 4/13. I already have on the left side. And so I'll have 4/13 times this entire side. And wow, now we're going to have it solved for that integral. Okay, well, 4/13 times 1/2 is actually 2/13. So we have 2 over 13 times e to the 2x power times cosine of 3x. Now we're going to multiply 4/13 times the second term, so we have a 4/13 times a 3/4. And when we do that, we get a 3/13 times e to the 2x times the sine of 3x, and finally, plus our constant of integration. So we have now calculated the integral of e to the 2x cosine of 3x. And we did that by solving for the integral. We ended up with that integral on both sides, and because it was on both sides, we can gather the terms or the integral to one side. We solved for that integral. Now, of course, again, that was only worked because this was a minus sign. If that would have been a plus sign, well, I guess it would have been all right if it would have been a plus sign as well, as long as our two integral sides are not exactly alike. So when we added or subtracted, we didn't get 0. So we were fortunate there that this does work. This is a new technique for us. We still used integration by parts, and we used it multiple times. Now, the next page. In this particular case, we used the light idea, but as we started this whole section, what I said is that you choose the dv to be as complicated as possible, but where you could still integrate. You know, in choosing dv to be e to the 2x dx, or choosing dv to be cosine of 3x dx, I can't say that one of those is particularly more difficult than the other to integrate. They're both things that we can integrate pretty easily, and if we choose u to be e to the 2x, we can differentiate that pretty easily as well. So I really suggest that you stop the video right now and you continue this process while we're at it. You try to practice this process by making a different choice for dv and a different choice for u than we did originally. Now, let me also, this is not the only case, but let me point out the forms that require this technique. The forms of integrals, and in the next section we'll even see some other forms which will require this technique. Forms of integrals that require this technique. And it would be integrals like this. The integral of e to some power constant times x as the power of e times the sine of some constant times x. Okay? And in this case, the last case, our a was 2. Well, it's actually, we had the cosine, didn't we? So another possibility is e to the a times x times cosine of bx. In other words, when we have e to the power times sine or cosine in our integral, this would be these would be perfect examples where we have to use the technique that we just saw. The next example, let's turn the tables a bit. We're still going to use integration by parts, but we're going to look at maybe something a little more interesting, that is an area. Let's calculate an area. In this problem, we're asked to, as you can see, we're asked to find the area under a curve, and the curve is y equal natural log of x, and we're finding the area from x equal 1 to x equal e. So just quickly a little sketch. Okay. Now remember, logarithm curves in general the simple logarithm curves is when x is 1, then the natural log of 1 is just 0. So 1 comma 0 is on the curve. And then as a reminder, this curve looks something like this then. Okay. That's what the curve looks like. So this is where 1 is. And E would be out here someplace. E is about 2.7. So here's where E is. And so what we're really doing is we're finding the area right in here. So of course the way we find area of something like that would we simply integrate, don't we? So we would integrate y, okay? We're just integrating under the curve f of x or y. So we're integrating the natural log of x with respect to x from 1 to e. Now, to be able to do that, we've got to be able to come up with the indefinite integral. And so our issue right now is what's the indefinite integral of natural log of x with respect to x? That's a problem. We haven't ever seen that. We've seen where an integral gave us a result of natural log of x, but we've never integrated natural log of x. Now, as we begin to investigate this, we only have one function, and we're used to, of course, we're in the integration by parts section, aren't we? And we're used to trying to use integration by parts and assuming that we have two functions. That's what we've assumed each time. Now, I'm not sure how we would go about this here, or yes, I am, but the problem is that we don't have many choices. And if we choose dv to be the most complicated thing we can have, and that's the natural log of x with respect to x, of course, then there's nothing left at all, is there? So there's a little twist to this one. What I'm going to do is I'm going to choose dv to actually just be dx. And I'm going to choose u to be natural log of x. And of course, then the integral of dv is just v, and the integral of dx is just x, so we have v is equal to x. Now the significance here is we can find the derivative of natural log of x. We couldn't. We weren't in a position to find the integral, but the derivative is just 1 over x. So du is 1 over x dx. Well, now we're set because the integral of natural log of x with respect to x being in the form the integral of u dv for our proposed u's and v's there, well, that's uv minus the integral of v du. And u in this case is, of course, natural log of x, and v is x. So let me write it as v first, and then u. Just looks a little better. Minus the integral of v, which is x, times du, which is 1 over x dx. And we have such a nice simplification here. X times 1 over x is just 1. So this is x natural log of x minus the integral of dx, which is just x, isn't it? And of course, normally we would have plus a constant of integration. Well, I want you to remember this technique, whether you remember the results, but remember the technique. This is special, okay? This is kind of special. We had a little twist, but now we're in a position to go back up here and calculate the area, because we know the indefinite integral is x natural log of x minus x. That's the indefinite integral, and so we need to evaluate that from 1 to e, don't we? Well, we can go about doing that. First, we substitute in an e, okay? So we'll have an e times the natural log of e minus e. And then we'll substitute a 1. We'll have 1 times the natural log of 1 minus 1. Now, the natural log of e is just 1. So this is e times 1 minus e, which of course that's just 0, isn't it? Over here, the natural log of 1 is 0. So we have 0 minus 1 in this position. So we have a 0 here and a plus 1 on the right side, and so the result here is 1 square units, whatever they are, whatever our units are. So that particular, actually that's a famous result, very important to understand at other times in calculus, that that area is 1. Well, let's do another problem related to this or similar to this that's a volume rather than an area. Okay, in this problem, we've got R is the region bounded by the graph of y equal natural log of x, the x-axis, and the line x equal a, where a is some value bigger than 1. And we're to find the volume of the solid that we get when we revolve this region about the x-axis. So real quickly, again, a sketch. Okay, we've got this graph of, let's say this is where a is, this is where 1 is. And of course, the natural log function looks like this, doesn't it? But we're only interested in the part of this that's under the curve, bounded by the x-axis and the line x equal a, which is that vertical line. And then we're going to rotate that about the x-axis. And so when we do, we're going to get something that looks, kind of like well, that's not a very pretty graph, is it? But we're going to get some solid that looks kind of like that. Okay. So, remember how we set this up. The volume will be the integral of pi times r squared times the height, which is actually our dx here. And we integrate from 1 to a, where we start our value 1 to we stop a. Remember, we're actually cutting out disks. See, we're actually cutting out disks of this. And when we look at that disk, if you remember, okay, we're looking at the volume of that one little disk. And this measurement is the dx. And the radius of this, okay, we have here. And what else do we need? Oh, okay, well the volume is the area of the base, which is pi r squared, times the height, which is dx. So that's where that comes from, as you recall. And we're adding up all of those different volumes by integration. So what we end up with here is the integral from 1 to a of pi. Oh, and by the way, that r is this measurement from the x-axis to the curve. So that r is actually just the natural log of x, isn't it? So it's r squared, that's the natural log of x, but that's being squared, not the x. The natural log of x is being squared. So don't put that square down here on the x, dx. And so that's a matter of integrating. Well, we could factor out that pi, couldn't we? From 1 to a of the natural log of x squared with respect to x. Well, this is the kind of problem that we've had in the past. We don't know how to integrate natural log of x being squared. Maybe integration by parts would work, and if we do this similarly to what we did a while ago, let's consider only the indefinite integral. And if we consider only the indefinite integral, why don't we choose our dv like we did a moment ago to be dx? And so v is just x. And why don't we choose our u to be the natural log of x being squared? Now, the issue here is when we find du, we have to use the chain rule. We have to bring that exponent 2 down, and then it's times the natural log of x to the first power. But remember, we were using the general power rule here, if you will. that now we have to take the derivative of the insides. And the derivative of the inside of what that power was on is natural log of x. So when we take the derivative of natural log of x, we get 1 over x. And of course, that's all multiplied with dx. So du, after we do some simplification, is really 2 times the natural log of x, all divided by x dx. That's our du. Okay, so the integral of natural log of x being squared is u times v. And u is that natural log of x quantity squared, and v is x. I'm going to write that in front. So it's x, and I'm going to get rid of the brackets and the extra baggage here. It's x times natural log of x being squared minus the integral of v du. Now v is x, and du is this fraction times dx. It's 2 natural log of x over x dx. But we have cancellation there, don't we? We have cancellation. So we have x times natural log of x squared minus, now the x's cancel, and we have a factor of 2, we'll factor out, so it's 2 times the integral of natural log of x dx. Oh, we don't know how to do that, but we just did on the previous page, didn't we? So we go back and look, or if not, we have to use integration by parts again. But we go back and look and say, how did we do that? Let's see, how did we do that? Oh yes, here's what we got. So first we have our x times natural log of x squared minus 2 times, and when we integrate natural log of x, we got, I've forgotten, what do we get? Oh yeah, we got x times natural log of x minus x. That's what we got when we did that integral on the previous page. Well, that's just a matter of being convenient. Otherwise, we would have had some work to do, wouldn't we? Now we're going to distribute that -2, so we have -2x natural log of x, and then -2 times -x is plus 2x. So here's where we are. We've got the indefinite integral of that integral of natural log of x all being squared. And so what we need to do next is we need to evaluate that indefinite integral. So here's where we are. We have this pi. The indefinite integral is x natural log of x being squared minus 2x natural log of x plus 2x. That's the indefinite integral, and we have to evaluate that from 1 to a. Well, when we do that, when we put an a value in, we'll have a times the natural log of a, but that's squared, minus 2 times a times the natural log of a, plus a 2a. A 2a. Now, when we substitute a 1 in, whoops, my bad. I got ahead of myself. I better put parentheses here. When we substitute a 1 in, we'll have 1 times natural log of 1 squared, but natural log of 1 is a 0. So that's just a 0 in the first position. I've run out of space. And then we have minus 2 times a 1 for x, and a natural log of 1 for x. The natural log of 1 is 0. And so we end up with a 0 in that position. Finally, plus a 2 times 1. Remember, our x was 1. And so that ends up being a minus 2. So here's the result. We have pi times a times the natural log of a, and of course that's squared. And I'm using parentheses and brackets. Minus 2a times the natural log of a plus 2a minus 2. That's the result of it. Now, if we knew what A was, we could certainly calculate the volume. We've just done this in a general way. I'm sorry that got a little messy there, but this is the volume, depending on the value of A. Okay, I want to close out this section with one more example. We've seen lots of examples here. This one has a little bit of twist on its own again, just because it's maybe not so easy to do. So let's look at that example. Okay, here we're asked to evaluate the integral of x divided by the square root of x plus 1 with respect to x. And we might find several methods of doing this, but the reason I'm choosing to do this problem here is to show you, one, that we can employ integration by parts in more than one way, and it doesn't always have to be a product with a transcendental function. Clearly we don't have that here. But we're still kind of miffed with how we're going to choose our dv and so on. And, and I'm looking here and thinking that if we're going to break this into pieces, our dv could be 1 over the square root of x plus 1 dx. So I'm going to write that as x plus 1 to the power negative 1/2 dx. It could be that. We could choose our dv to simply be x dx. We could choose our dv to just be dx, but that would be silly because that would be more or less what we're trying to integrate anyway. I take that back. That wouldn't be what we're trying to integrate. That would be, but our differentiation would be kind of complicated. And anyway, I'm mumbling here. I apologize. Since this doesn't really fit the Lie-8 combination, because those have to do mostly with transcendental functions, and we don't have any transcendental function here, so we can't really see what comes first. So I'm deciding to use the most complicated thing for dv that I think that I can integrate, and that seems to be it. I think I can integrate that. So I'm going to choose dv to be x plus 1 to the power negative 1/2 dx. And that means that u is simply going to be x. Well, let's get that out of the way then. If u is x, then du is dx. The problem becomes a little bit calculating v. So v is the integral of x plus 1 to the power negative 1/2 dx. Now, separate from, I guess we need to call it something else, but we can do this by substitution. And we normally called it u substitution, but since I'm already using plenty of u's, let's call it w. We can replace x plus 1 with a w. And if we do, then dw would simply be dx. And so this would end up being the integral of w to the negative 1/2 power dw. And that's easy for us to integrate. What we'll do is add 1 to that, so we'd get a power of positive 1/2. Of course, we have to offset that with the reciprocal. And of course, w is nothing more than x plus 1. So this is 2 times x plus 1 to the 1/2 power, which of course is the square root. So now we have our v, we have our du, we're ready to integrate. The integral of x divided by the square root of x plus 1 dx. And of course it's still a drum roll because we're not sure what integral we're going to get when we apply integration by parts. But integration by parts will be an a u times v. So that's an x times a 2 times x plus 1 to the power 1/2 minus an integral of v du. Well, v is 2 times x plus 1/2 to the x plus 1 to the power 1/2. du is just dx. And I think we can integrate that in a way that in a fashion similar to what we did. Here we're going to rearrange first. Instead of saying x times 2 times, we'll say 2x, and we'll write x plus 1 to the 1/2 power as the square root of x plus 1. Minus, we'll factor out that factor of 2, and so we're integrating x plus 1 to the power 1/2 with respect to x. Well, we could do the same thing. We could let w be x plus 1, and so we would be doing nothing more than integrating w to the 1/2 power dw, because we would also get dw to be dx. So as we look at integrating here, let's see, as we did that, we would have to increase the power by 1, so that would give us a power of 3/2, wouldn't it? So that'd be x plus 1 to the 3/2 power, and we'd have to offset that with a reciprocal, and then of course we'd have the constant of integration at the end. So we can do several things in writing this. This is 2x times the square root of x plus 1, and that negative 2 times 2/3, of course, is a negative 4/3 times x plus 1 to the power 3/2. And then we could write that differently if we so chose. Okay, because that's nothing more than the square root of x plus 1 to the power 3. That's our constant integration. Now, of course, all along we're assuming x plus 1 is positive, otherwise we would have had the square root of it. And so that allows us to simplify that expression if we so desired, because we really have x plus 1 squared times x plus 1 under the radical. Well, the square root of x plus 1 squared, since we know x plus 1 is positive, is just x plus 1. And so we still have the square root of x plus 1 in that case there. So this is another way to write that, and there's still more algebra we could do. But the main point here, of course, is we didn't have a transcendental function, and we could employ this technique to integrate something with the integration by parts idea. Well, that's all for this section. Good luck on your homework. I'm sure you'll do well, but it will take a little bit of work.